Good morning, everyone. I just want to introduce Dr. Ronald Tackett. Dr. Tackett is a professor at Kettering University, a professor of physics. He was one of the faculty members involved in the, if you guys remember that glioblastoma project with the nanoparticles. So he was part of faculty that was working on that, from my understanding, the physics component of it. Dr. Tackett was also previously at Arkansas State University, or Arkansas Tech University as well. So we invite him today to speak at our facility, so we're very excited to have you.
Well, thank you very much. So I'm going to talk a little bit about that glioblastoma project today, and then talk a little bit about some of the things that have come out of that, at least moving forward. And a little bit of background about basically how things work. So to understand magnetic nanoparticles, we first have to understand a little bit about magnetism in materials in general. And essentially, there's three types of magnetism that exist in materials, and they're classified based on their response to an external magnetic field. And those are, and I apologize, it looks like we may have some issues here with some of the equations. But we have diamagnetic materials, and these materials are what nominally most people would consider non-magnetic materials. They have a very weak response that is characterized by what we call the magnetic susceptibility, which is roughly the constant of proportionality between the size of the field that's applied and the magnetic response of the material. And it's very, very small, around 10 to the minus 5 in these diamagnetic materials, and it lines up the magnetization vectors anti-parallel to the applied field. The next of these are paramagnets, and these are, in terms of what a layperson would speak of, what magnets stick, or what stick to magnets. So your refrigerator surface is a paramagnet, and that's why our refrigerator magnets stick to those surfaces. These, when we apply a magnetic field, the magnetization of the material aligns with the field, and it has a slightly larger response, 10 to the minus 2 to 10 to the minus 5, than a paramagnetic material, but still not a very large response. These are both what we call typically linear magnetic materials, in the fact that the response is linear. If you raise the magnitude of the field, the magnitude of the response raises in a linear fashion. What most people would consider magnets, though, are what we call typically ferromagnets, or sometimes anti-ferromagnets, or there's even ferrimagnets. But these are non-linear magnetic materials. We call them complex magnetic materials. These are the permanent magnets that you see around. These have a permanent moment. That moment, that magnetization, permanent magnetization, will respond to a field, and we can see its orders of magnitude above the response that we see from the linear magnetic materials, those being the paramagnets and the diamagnets. We're going to focus mostly on these types of materials today. Ferromagnets are mostly ferrimagnets. A ferrimagnet is where you have two different magnetic species within the material. And if you think of each one of these representing an atom in the material or a magnetic ion, the coupling is actually anti-ferromagnetic in a ferrimagnet, but the strengths of the two magnetic species are different, so you do get a magnetization. These are really weird. There's long range, what we call magnetic order, but they don't really magnetize because this guy cancels out that guy and so on and so forth. But if those arrows are different lengths, they don't necessarily cancel out. But if we look at these materials, again, why we call diamagnets and paramagnets linear magnetic materials is as we increase H, the magnetic field, the response of those is linear. in terms of magnetization. Now the ferromagnets exhibit this much larger response, but they also tend to saturate, okay? So there's a point beyond which you're not going to get any larger response, and we can see that obviously this is not linear. The other thing about these is they exhibit what we call magnetic hysteresis. If we scan from zero field up to here, and then we take the field and we scan it back down to zero, the magnetization doesn't go to zero. It's left with some remnant value. That's that permanent magnetization. Now we could complete this loop if we push it in the other direction. So if we start applying a field in the opposite direction, we can what we call coerce the magnetization back down to zero. The field that takes is typically called the coercive field. This we call the remnant magnetization of the material, what's left after we magnetized it, and that's the saturation magnetization of the material, or its maximum magnetization. The reason it saturates is the materials form these domains, and the most response we can get is by aligning all of these domains with the magnetic field. So in a typical ferromagnet that hasn't been exposed to a magnetic field in a while, we have all of these domains. They're pointing in random directions, and there's not necessarily an overall magnetization of the material. However, if we put a magnetization on, let's say to the right, those domains that are more aligned with the material or with the field grow, and the others shrink. It's what we call domain dynamics or domain wall motion, and this sort of governs the magnetic behavior of these. The problem arises when we start talking about really fine materials, meaning size-constrained or small materials. There gets down to a point where it's no longer energetically favorable to form multiple domains in a structure, and we have what we call a single domain particle, or a magnetic nanoparticle. And the behavior of these is fundamentally different than those of their what we call bulk counterparts, because it can no longer be governed by this domain wall dynamics because there are no domain walls. So what happens is these essentially behave paramagnetic, but on a grander scale, and we actually call the behavior superparamagnetism, where paramagnetism is describing ionic or atomic moments. This superparamagnetism is talking about the response of nanoparticles, so much bigger, mini atoms that are all sort of aligned in this. The magnetic behavior looks something like this. If we're looking at the magnetization as a function of time, this is how we sort of identify superparamagnetism. We typically run what's called a ZFC-FC scan on a magnetometer, which stands for zero field-cooled, field-cooled. So we initially keep the particles in no magnetic field, and they're randomly aligned, and we cool it down. And then we put a small magnetic field on in some direction, and we start measuring the magnetization upon warming. And these are governed by this thermally activated moment reversal. If there's enough thermal energy there, if they're warm enough, they can align with the field very readily. But if there's not enough thermal energy, they don't align. They're like squeaky hinges. And what we see here in the zero field cooled is as they start to unfreeze, we start to see this increase. And the peak here, what we call the blocking temperature, is about where half of the nanoparticles in your sample are free to rotate freely and align with the field. The bifurcation point here, which is the separation between the field cooled and the zero field cooled. The field cooled, after we do this curve, we just cool back down in the field, which aligns everything and then scan up. This is when all of your nanoparticles are unblocked and free to move into the field. But if you're looking to produce heat, convert magnetic energy into thermal energy, you want to operate right around this point. Think about opening and closing a door with a rusty hinge. If that hinge is nice and oiled, that door opens really fine. And if you touch the hinge, not a lot of heat. But if that rusty hinge and you keep opening and closing it, it starts to heat up at that rusty point because it's sort of stuck and we're unsticking it. Same idea. So we want to use this essentially to produce heat. So we make these nanoparticles. We typically have used iron oxide. The reason is we want to use these, or we have targeted these for use in a hyperthermia type treatment. Iron oxide, fairly biocompatible. So what we do is we take two donors. Essentially, this is an Fe3 plus ion donor. This is an Fe2 plus ion donor. We add a bunch of hydroxide ions. They react to form iron oxyhydroxide, which then through another reaction precipitates Fe3O4 or iron oxide. So what we're left with is these black particles that can be suspended in a fluid, typically water. We coat them with a surfactant so we can get them nice and far away from one another. They're not dissolvable in water themselves, but through steric repulsion, just the fact that the surfactants that we use have these long dangly ends that have charges on them. They don't like to be near one another. So they push away and they sort of fake these materials into believing that they're dissolvable in water. So what we can do is essentially produce a magnetic fluid, what we typically call a ferrofluid. So we characterize this. This is X-ray diffraction here, just showing that we did get Fe3O4. We did some imaging with transmission electron microscopy. So these are the nanoparticles themselves. They do tend to, without that surfactant, there's no surfactant on these here, aggregate a little bit, which will cause them to fall out of solution. But you can see this bar is 20 nanometers. You look here, we're at about 15-ish nanometers in diameter for most of those particles, and they're relatively spherical. This is a cross section, not perfectly, but this is a pretty quick and easy reaction that we've done. I train second-year undergraduate students to do this all the time. It's pretty simple wet chemistry. So it's a pretty nice way to be able to produce these. And there's all sorts of applications of these in the medical field in particular. The hyperthermia-based therapies is what we had been targeting, looking to actually treat malignant tissue with heat because of its increased metabolism of these tumors. They eat heat essentially more than healthy tissue, so they will die faster than healthy tissue. So if we can hold those tumors at this elevated temperature through the use of these, we can kill them off without really any harsh chemotherapeutic agents. However, there's other things that we can do. We can trap those chemotherapeutic agents in a sort of cage of molecules, and we can use the heat produced from hyperthermia to open that cage, which would then deliver that drug molecule. So the nice thing about that is we can get that drug molecule to wherever we want through antibody targeting or things like that without having it interact with the body until it's delivered to the place where we want it. So some of those side effects of chemotherapy, maybe we can reduce. All sorts of different things, using magnetic targeting even.
And that can be local then, right? So in other words,
Absolutely.
you exert the magnetic field on the brain, it's not going to be exerted anywhere else in the body.
That's
Reasonably
absolutely
speaking.
right.
So then those particles can stay contained.
Yep.
And then you can use higher dosages of chemotherapy.
That would be another thing that we could do, is exactly because we're it would be typically, I would think, injected similar to any other chemotherapeutic agent, but it would be given some time to then move through the body towards that before the actual treatment is released. So it is sort of a form of localized or targeted therapy.
Mhm.
But again, what we had been focusing on is this hyperthermia idea here, where we have this tumor with a nice blood supply here, and we take the idea that we were thinking at this point when we were collaborating was even looking to aspirate some of the internal necrotic core of a tumor and take that voided area that we've pulled out and fill it up with this magnetic fluid. And we would then expose that magnetic fluid to an alternating magnetic field. So one that's going back and forth. And essentially these things would start to shake. And as they shake, they would heat. The rusty hinge idea. And it's a way that we can locally heat just that tumor and hopefully not too much of the surrounding tissue. So again, processing these into a fluid, what we've typically been using is Dextran. It's a sugar molecule related to dextrose. Again, biocompatibility was a lot of the reason for the choice behind that. But it's this long molecule that has some charges near the end, and they tend to, through different ways, we put this dextran into a basic solution, and it causes these molecules to sort of unfurl or uncoil. And then as we take that pH back down towards neutral, they curl back up. So we put them in with the particles in that high pH basic solution, lower the pH, and they start to sort of coil back up onto the particles. So they sort of encapsulate the particles. This is a visualization from this paper in Applied Surface Sciences about how this actually works. But the main point of these dextran chains is to allow this to stay suspended in the fluid. Otherwise, these nanoparticles, you would shake them up and they would move around, but after about 5 minutes, they would all settle down to the bottom of the tube. But with the dextran, they stay stable for a much longer time. I've seen these materials stay in solution for months. They won't stay indefinite, but we have been able to stabilize them for a pretty good long time. So what we were looking to do was to target glioblastoma, a lot because of the case that it's fairly resistant to many other traditional treatments. So the idea would be to take someone who has one of these glioblastoma, inject into that tumor these magnetic fluids. We would then, and this is what we were working with a company in Auburn Hills, AMF Life Systems, I think, is their spin-off. I can never remember the name. What's the name of the company?
I think flexdraw.
Flexdraw.
Yeah.
Flexdraw is the name of the actual company, but they have this AMF Life Systems spin-off that they're an induction heating company, basically to look into these hyperthermia applications. They were designing this coil that could be lowered down over the head, and that coil would produce an alternating magnetic field, and that alternating magnetic field would typically be in the radio frequency range, somewhere between 150 to 300 kilohertz, with a very small amplitude in the millitesla regime. And we can start to heat that tumor and hopefully induce necrosis in there. Now that's the sort of treatment modality. I'm a material scientist, so my interest is to study how does this actually produce the heat. So we want to know everything about how this mechanism works. So when we're looking at these particles, when they respond to a field, there's sort of two ways that they can do it. So if you think of a fixed particle, one that cannot rotate. So if we think about putting it in that water and then freezing the water, the only available mechanism for the nanoparticle to align its moment with the magnetic field is internally. The particle's fixed. It's what's called nail relaxation. But it's dependent on what the material is, what the nanoparticle is made of, the size of the nanoparticle. I apologize, these equations got kind of messed up, but this is an Arrhenius type equation. I'm not sure if you're familiar with that, but it essentially is what describes thermally activated processes, okay? So it's saying that there needs to be this much energy present, thermal energy, for this to happen, okay? And it's dependent on temperature. That's this T here. This kV is a constant. But it's also dependent on the volume of the nanoparticle, so how big it is. And K, which is the magnetocrystalline anisotropy, say that 10 times fast. But it's related to the structure of the material and how many materials like to be magnetized in a certain direction relative to their crystal structure more than, say, some other direction. And we quantify it with this number. The other is what we call Brownian relaxation, or simple Brownian motion. In a fluid, all of the molecules are sort of moving around, and that's called Brownian motion. So you can think of the particle actually physically rotating to align the moment, the magnetization, with the field. But this is less nanoparticle dependent and more carrier fluid dependent. It's dependent on this eta, which is the viscosity, how thick is the fluid. V sub H is a little different than V sub M. V sub M is the magnetic core volume. V sub H is what we call the hydrodynamic volume. It's the magnetic core plus that Dextran shell. And it has a small temperature dependence as well. So what we look to do is run experiments to see how these things heat. So we have a small induction heater, has a maximum output of 2.4 kilowatts. So what this is just an amplifier circuit that's connected to what we call an LC circuit that's run at some resonance. We pump about anywhere from 100 to 200 amps of current through that coil, and it creates a pretty strong magnetic field at the center, and the current is alternating, so it flips that magnetic field direction. And we measure the temperature of the fluid using an optical method. If we were to put a metal thermocouple in there, it makes the thermocouple go crazy. So what we have here is this optical thermometer. It's a fiber optic that has a small gallium arsenide crystal, which has a temperature-dependent band gap, if that makes any sense to you. And as that changes, it can monitor temperature. But for all intents and purposes, it's a really fancy thermometer that uses light instead of the way that a typical thermocouple uses metals and works on current. So we can measure what's called the specific absorption rate, which is essentially the slope of that line there. But what it's related to is how good are these nanoparticles at converting energy from the magnetic field into heat, which is what we want to use. So if we look here, these are some Fe3O4 particles in this solution. We ran this experiment for almost 20 minutes, and you can see it took us from about room temperature, 25 degrees C, up to about 42, 43 degrees Celsius, which turns out to be that magic temperature. Somewhere between 40 and 45 is probably a little bit big of a window. We can narrow that down a little bit, but there's a magic temperature that will kill the tumor, but not cause much damage to surrounding tissue. So that's what we're looking to do, looking to determine these. So this is some work we've done. I've been working in this since around 2005. This is some data from a paper we published in 2008. This is some data that we published in 2015. What we're looking at there is that experiment that I described, taking that particle solution, that magnetic fluid, and freezing it. So we froze it with liquid nitrogen. You can see that we're at really low temperatures here. So now we're looking at only the contribution to that specific absorption rate from the nail relaxation, because we've essentially rendered Brownian motion null by freezing the material. If you're interested more, there's the paper, but we found some pretty good results, and things were pretty good. So what we turned to is actually looking at some other materials besides iron oxide. So remember I told you that magic temperature is somewhere between 40 and 45 degrees Celsius. Well, with iron oxide, they're what we call paramagnetic to ferromagnetic phase transition occurs up in the 1,000 degrees Celsius range. So if we keep driving those particles, they will heat right up to 1,000 degrees Celsius, burn the building down, melt everything in its path. We don't want that. But if we can use this phase transition here, when they come from ferromagnet to paramagnets, their response goes down by several orders of magnitude. They're not going to generate nearly as much heat. In fact, they don't hardly generate any heat at all. So this is a way that we could turn it off at a specified temperature without having to put something else into the body to monitor that temperature, right? We want to be as least invasive as possible. So we're calling these sort of smart particles that have this, what we call Curie temperature, right at that magic range. So what we could do here is then just drive the magnetic field as hard as we want, and these will heat up to that, and then they'll just sort of hover around that temperature. As they go above it, the magnetism essentially shuts off, cools down a little bit, comes below it, it turns back on, heats up.
It's like 45 degrees. Is what you're thinking.
Well, somewhere around there. So what we turned to were these manganate systems. So if we take lanthanum manganate, lanthanum being a magnetically active ion, and we dope it with non-magnetically active ions, in this case looking at barium, calcium, and strontium to put here on this, then what we can do is see if we can adjust that amount of that non-magnetic ion and tune that transition temperature. And that's exactly what we did. So we synthesized these things. We shown on the previous slide the method. I always really like this picture. This was one of the first pictures that we took with our TEM that we got a couple years ago. And the reason that I like this is it's kind of neat. These things self-assemble into these sort of hexagonal shapes. But also, this is probably at around 1.5 million times. I don't think that number is right. These lines that you're seeing here, that's planes of atoms. And I always think that that's so cool that we can have a microscope that can see at that level of precision. Again, here we were just looking at, is the crystal structure of these correct? Did we make what we think we were making? So we took these and we sent them out to our collaborators at South Dakota State who have a magnetometer. And essentially what we did is we measured this temperature, where both these ZFC and FCs come down and go to 0 is what we call the Curie temperature. It's that transition temperature. And what we've done here is plotted that transition temperature versus the dopant amount. And again, that 45 is the magic number, so it doesn't look like the barium and the calcium are going to help us much, because if we go much past 0.25, we mess the crystal structure up. It can't take that amount of impurity atoms. But the strontium doped one is really promising, and we have this fairly linear response to doping and Curie temperature. So if we were to draw a line right here, and 45 is that magic temperature, it turns out right around maybe 0.18 to 0.22, or 18 to 22% of the lanthanum atoms being replaced by strontium atoms in the structure is where we would want to be. And we've since started making them at that, and these things do heat up to a point. I can't show the data yet because we're just in the last stages of publishing it. But they will actually shut off and hold at that temperature. So it's very promising in that field. The very bad part about these is I don't think you want to put lanthanum manganate in your body with that heavy metal lanthanum. So these are not real biocompatible. So our next step, I'll come back to this. Our next step is to look if we can maybe coat these and make what we call a core shell nanoparticle. So we'll have that lanthanum or strontium doped lanthanum manganate in the core. And what we'll coat this with, we've already got the magnetic species in the core. What we'll probably try to coat it with is silicon dioxide, SiO2, sand, essentially, which is relatively biocompatible. And the whole idea here would be to isolate those heavy metal ions from leaching into the body, coat them with something that will hold those in there, but not affect the magnetic response that much. So that's what we're currently working with.
And ultimately they're excreted then, you're saying?
Yep, that would be the hope. On a side note, it turns out there's some other stuff that goes on here. This is change in entropy. This is getting a lot more material science-y, and I don't want to spend too much time here. But at the right dopings, these things show what we call this giant magnetocaloric effect. So they absorb heat like crazy. And they're really starting to turn out as promising candidates for what we call magnetic refrigeration, which would be a more energy efficient way to cool. So for houses and things like that, if you're interested, this is a paper that just came out about a couple weeks ago that we wrote on this in Materials Research Express. And you can take a look at that. But that's basically it. I didn't want to take up too much of your time today. But thank you for the invitation. It's always nice to come talk about this stuff and see what people are doing.